Hi everyone, this is for the beginning of Module 4 for your reading this week. I have a memory verse. He is before all things, and in him all things hold together. Colossians 1:17, and you're going to be talking about how things hold together with different kinds of bonds, chemical bonds. Don't forget to do your study guide for Module 3 to get ready for the test. Use those study guide answers to go through the questions. So your book talks about chemical formulas, a way of writing compounds showing the ratio of elements within the compound. Okay, so remember a compound is two or more atoms held together. And so we have 1 nitrogen and 4 hydrogens in ammonia. And this is the subscript right here, which we'll go over in a little bit. That tells you how many of each atom you have in the chemical formula. And then so in H2O you have 2 hydrogens because the subscript is a 2 and 1 oxygen. Okay, and then it talks about chemical equations. So the chemical equations use the chemical formulas to describe what is happening in a chemical reaction. So there's something changing. So the reactants are the ones that are changing, and the products are the new substances that are formed after the reaction happens. So you would start with carbon and oxygen, and you'd end up with carbon dioxide after the reaction. So these are completely different than carbon dioxide. Same with like water. You have hydrogen and oxygen gases, and then it reacts to form a liquid. And then there's such thing as homonuclear diatomic molecules. So that would be like your oxygen molecules. They don't exist in nature by themselves. They like to be bonded together with each other. So you'll always find them as 2 atoms joined together with a bond. They're called homonuclear because they have the same nucleus. Homo means the same, and nuclear for the nucleus. And then there's 2 atoms, diatomic. So it's a homonuclear diatomic molecule. So you guys are going to learn how to balance equations. That means making the same number of the same type of atoms equal on each side. Okay, so for this reaction, these are the subscripts right here, and you cannot change a subscript. Okay, this is 2 atoms bonded together. So if you want more of these, you're going to get, if you put like a 2 here, you would get 2 times 2, and that would be 4 oxygen atoms. You can never get 3 oxygen atoms out of this molecule because these are bonded together. So you can't ever change a subscript. You can add coefficients. So coefficients are numbers that appear before a formula in a chemical equation to show how many atoms or molecules of each reactant or product are involved in the reaction. So let's try to balance this out. I like to use tally marks. Some people will write a number like 2Fe. Sorry, I wasn't looking at what I was doing. Fe. I just like to use tally marks, so we're going to do it this way. Okay, so we have 1 iron atom, and we have 2, hopefully you can see that, 2 oxygen atoms. And over here, we have 2 iron atoms and 3 oxygen atoms. So we have to figure out what we can do to this to balance them out. Okay, so let's say to make nice round numbers, I'm going to put a 2 here, and then let's see what we have to work with, okay? So 2 times 2 is now 4, so we have 4 irons over here. 2 times 3 is now 6, so we have 6 oxygen atoms over here. We're counting the atoms, we're not counting the molecules. And then over here, we have 1 iron. So what are we going to do that to make 4? We're going to have to use a coefficient over here. So we're going to put a coefficient of 4 in front of the iron. And so that's going to give us 1, 2, 3, 4 iron atoms over here. Okay, so we have 4 here, 4 here. That is balanced, but the oxygen is not balanced. So let's balance the oxygen. So we have 5 over here, and we have 2 over here. Let's try, sorry, we don't have 5. We have 6. 2 times 3 is 6. I just didn't put that 6 tally mark. Let's try 2 times 3 over here. 2 times 3, or 3 times 2, is 6. And then we have the same amount of oxygen atoms and the same amount of iron atoms, and we have a balanced equation. So that's what you're going to do to balance the equations. So you can do that with this one too. This one's pretty simple. There's 2 hydrogens here, 1 oxygen here. There's 2 oxygens here and 2 hydrogens here. The hydrogens are already balanced, and then we need to balance the oxygens, so we put a 2 here. And so then we have 2 oxygens. That balances the oxygens. And now we need to go back and fix the hydrogens. So we have 2 times 2 is 4 now. And so we're going to have to put a coefficient right here. And that makes 4 here. And so what this actually means is that when the chemical reaction is occurring, it's using twice as many hydrogen atoms to create the reaction to make it work than oxygen atoms. And we're going to do an experiment later on in class that will show you this in a better way. So to talk about the 2 basic kind of bonds that atoms make, the ionic bonds and the covalent bonds, let's just explain what an ion is. So if you take a normal sodium atom, as you can see the valence electron out here, this is what's going to do the reacting. And to get that octet rule of 8 right here, it doesn't apply to the first energy level. That's always 2 electrons, but in the second energy level, it wants to have 8. Well, actually, atoms don't want anything, but that's what naturally occurs. So this valence electron, it's going to leave easily. And then if you have, let's say, chlorine, this has 7 valence electrons, and so it's going to naturally want to attract 1 more electron to fill its energy level with 8 electrons. And so what they do is to bond together. Actually, let's back up. We won't do that yet. If this chlorine gains an electron, it's neutral. Its net charge is 0 when it has the 7 valence electrons. When it gets another electron, electrons have a negative charge, so it's actually going to have a +1 net charge when it gains an electron, and then it's an ion, okay? It's an atom with a charge, okay? And same thing with sodium. It has that extra, the valence electron right here. When it loses that, it's losing a negative charge, and it's going to do what? It's going to have a positive charge, a +1 charge, because it lost 1 negative electron, but it still has the same number of protons that are positively charged in the nucleus. Now, to do an ionic bond, these two want to, they're not exactly sharing, but one loses an electron and one gains an electron. And so sodium and chloride, NaCl, that's table salts, and that's an ionic bond that they have. Okay, I hope that makes sense. So this, as an ion, becomes positively charged. This becomes negatively charged because it's gained an electron, and they can make an ionic bond together. And just remember that the noble gases, they don't really react very much. They can. It takes a lot of energy, though, because they're just content to stay the way that they are. Their valence electrons are 8, and they don't need to gain any. They don't need to lose any, and so they're very stable. If you guys do the salt crystal at home, bring it into class. I would love to see it. Okay, when you come to page 126, it talks about the electron dot diagrams, and when you're filling them out, just make sure you are making them nice and neat so you can see where the valence electrons are matching. So this one's kind of on the bottom, this one's kind of on the top, and you can see this one fills in nicely, that octet, the 8 right there. I'm pretty sure this is a typo. Because you didn't take any protons away, you didn't create nitrogen, it's still sodium. So I think it's supposed to look like this, with the sodium having the positive charge and the chlorine negatively charged. And then this next dot diagram in your book, it shows magnesium chloride. So there's 2 chloride atoms for every 1 magnesium atom. And this is kind of how it goes. The magnesium is giving away 2 electrons, and each chlorine is taking 1 electron. And so this becomes, the magnesium becomes positively charged by 2 because it's lost 2 negative electrons. And the chlorine, becomes negatively charged because it's gained an electron and gained an electron. Your book has this nice table to show you how to draw the electron dot diagrams for different elements. Whenever they have 1 valence electron, that's how you're going to draw it. 2 valence electrons, 3 valence electrons, 4, and then you're going to kind of start matching them up in pairs. These are the noble gases, so they'll have 8 around them in pairs. Okay, so covalent bonds are a little bit different because 2 atoms are sharing 1 or more pairs of valence electrons. Okay, and it's happening between nonmetals. With the ionic bonds, 1 was giving up an electron or 2, and 1 was gaining an electron or 2. And those are happening between the nonmetals and the metals. Okay, so for covalent bonds, with the nonmetals, they're actually going to share electrons. So hydrogen has 1 valence electron, and so they like to share a valence electron to complete that first energy level, because the first energy level holds 2 electrons. This is chlorine, and I'm always getting chloride and chlorine mixed up. Chlorine, and so right here it's sharing its valence electrons. So chlorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, and 7. And so each of these has 7 valence electrons. They can share 1 valence electron in a bond to complete their octet so that they each have 8 valence electrons. And you can see that with the electron dot diagram. So there's 7 valence electrons here, 7 valence electrons here. There's no charges, okay? They're not losing them, but they're sharing them right here to make them equally happy, both of them. To make it a little bit easier to show covalent bonds, there's the structural formula model for a molecular compound. And so instead of using the dot pairs, they've replaced it with a dash to show the covalent bonds, like in methane, CH4, yes, CH4, methane. So it would have the covalent bonds as dashes. Now this comes in handy when there's more than 1 bond to show. Okay, so think about nitrogen. It's a group 5A element. It has 5 electrons in its outer energy level. If 2 nitrogen atoms each shared 1 electron, they would still only have 6 valence electrons. Okay, if they shared 2 electrons, they would still only have 7 valence electrons. But if they shared 3 electrons, then they would each have the 8 valence electrons needed for a stable electron configuration. And so that's called a triple bond. So you can see there's this is 5 electrons. There's 3 electrons here. There's 3 electrons here, and they're going to share. And so there's actually going to be a triple bond because they each need 3 more electrons to get their 8 and become stable. So far we've been talking about equal bonds, equal attraction for the shared electrons. It's been pretty easy. These guys are attracted to these guys. They're about the same. Okay, we did one with magnesium and chloride. They're of the same period. And so they're going to be, sorry, here we go. The left is attracted to the right, except for the noble gases, because those are a stable configuration already. Okay, so what if we talk about when they're not equally shared, the electrons are not equally shared? You can kind of see this is the ball and stick model, which shows basically that the electrons have a greater affinity to the larger positively charged nucleus. So obviously chlorine has more protons in its nucleus. And so they're going to make that bond, the hydrogen and the chlorine. But the electrons are going to spend more time near the nucleus of the chlorine atom. And so it's shown with this ball and stick diagram as this being larger here. So when you have this unequal sharing of electrons, you come up with a polar covalent bond. So a polar molecule is a molecule that has a slight positive and slight negative or slight negative charge due to an imbalance in the way the electrons are shared. Okay, so this is actually inaccurate because there's a little symbol in your book that shows a partial charge. It's not a full charge. So this is an oxygen molecule, and it has a partially positively charged side to it and a partially negatively charged side to it. So it has polarity. You can see here that oxygen has 6 valence electrons. Hydrogen each have 1 valence electron. And so the bonding is happening here. But remember, because the oxygen has more protons in its nucleus than the hydrogen, the electrons are going to spend more time moving around the molecule near closer to the oxygen atom's nucleus. And so because the negative electrons are closer to the oxygen, that's how you get this polarity, where there's a slight negative charge on one side of the molecule and a slight positive charge on the other side of the molecule. So polarity simply means having opposite charges within the same substance. There's a fun experiment you can do it at home. I don't think I'm going to be able to do it in class. It involves a balloon, and you need a stream of water to make this work, but it would be really fun if you did it at home, or maybe I can find a video with it. So now we know that water molecules have a partial negative charge on one side and a partial positive charge on the other side. And because of this, water can attract 4 other water molecules to it using hydrogen bonding. So hydrogen bonds are bonding that occurs in any molecule in which positive hydrogen atoms are attracted to negative atoms of nearby molecules. So in the picture here, you can see this hydrogen atom is attracted to the partial negative charge of this water molecule, and this hydrogen, same thing, and then this hydrogen is attracted to the partial negative charge of this water molecule, and same thing with this. So there's not actually a chemical reaction going on here. They're just attracted, kind of like magnets, although it's not the same as magnets. It's a hydrogen bond here. And then also just note that the hydrogen bonds are bonds that form between molecules and not between atoms. So water having polarity to it is what causes things to dissolve, so solubility. So remember that when you put a solid in, the solid is the solute, and the liquid that you're dissolving in is the solvent. Okay, so if water's our solvent and our solute is sodium chloride, which is table salt, remember that this is an ionic bond. So the sodium would have a positive charge to it, and the chlorine would have a negative charge to it. And so the polarity of the water molecules are attracted to that, and they can actually pull these atoms apart. And so the negative side of this is the oxygen, and these are the little hydrogens. The negative side of the water molecule is going to attract the sodium ion and pull it apart. So you get sodium ions and chlorine, I think it's chloride ions within your solution, okay? So the sodium's still there, but its ions are so far removed from each other that they exist on their own, and you wouldn't be able to see it. It'd be dissolved into the water. In talking about charges, we have positive charges that are coming from this side of the table. So these usually form a +1 charge. This is a +2 charge. Over here we have -1 charge, -2 charge. So these over here are negative, they're called cations, and over here are the anions. And then you can also have molecules that are positively charged or negatively charged. So this is an ammonium ion, and this is a cyanide ion. So cations are negative, anions are positive. This page here talks about something important. Why is water a liquid at room temperature when other chemicals similar to water are gases? So it's because of these hydrogen bonds. It holds so tightly together that it forms a liquid. The other ones that are that shape are actually gases, and there's such a small electronegativity difference between the sulfur and the hydrogen, so they can't polarize their bond and do what which H2O can do and become a polar molecule. So these are not actually hydrogen bonds. There's only 3 atoms that do hydrogen bonds: fluorine, nitrogen, and oxygen. And if you look on the periodic table, all of those have different valence electrons. So fluorine has 7 valence electrons, and nitrogen has 5 valence electrons. So when they bond, they don't even make that shape to make a polarized molecule. So hopefully that makes sense, because in the experiments upcoming, it's going to be really important to know that water has polarity. Okay, thanks for listening and watching.